Hi. Hi, welcome to chapter number 4, Organic Compounds, Cyclocanes and their Stereochemistry. Remember that this is a summary lecture, it's not in replacement of the live lecture. Okay, during this lecture we will talk about cyclocanes basically in their stereochemistry. We will name cyclocanes, we will talk about cis-trans isomerisms in cyclocanes, I will talk about the stability of cyclocanes, the grain strain, conformations of cyclocanes, conformations of cyclohexane, very important, for example, for sugars, axial and equatorial bonds in cyclohexane, conformation of monosubstituted cyclohexanes, and conformations of dissubstituted cyclohexanes. Okay? One important thing is that the most organic compounds contain rings of carbon atoms. Most pharmaceuticals and drugs or biomolecules contain rings. We need to understand the consequence of cyclic structures, basically the conformations possible. Naming cyclohexanes, this will be easier. Saturated cyclohydrocarbons are called cyclocanes or alicyclic compounds. Okay, for example, here we have three examples. A 3-member ring, a 4-member ring, a 5-member ring, and a 6-member ring. How are called? Basically are called with the same name than linear alkanes. This is 3, that means that has to be propane. This is 4, has to be butane. This is 5, has to be pentane. This is 6, has to be hexane. But with the cyclo just before. Okay, with the cyclo name just before. That means that this will be cyclopentane, this will be cyclobutane, this will be cyclopentane, and this will be cyclohexane. Okay, how we name it? Well, as usual, we have to find the parent, the most important carbon chain. In this case, it's easy because we have a 5-member ring cyclic and 1 methyl here. That means this will be cyclopentane substituted with a methyl cyclopentane. Okay, because it's cyclic, I don't need to put the number because any place where I put the methyl will be the position 1. But what about here? Here what we have is a 3-member ring and then 4 atoms, 4 carbons in a row. Obviously the most important chain will be the 4 atoms, as you can see here. That means that this will be butane, and then we put the substituent 1 cyclopropyl. Okay, here we have to put the number because obviously the first position of the butane is not the same than the second. Step 2. We number the substituents and write the name. We dispose a point or attachment as carbon 1 and number the substituents on the ring so that the second substituent has the lowest number possible. Here we have an example. Okay, we have here methyl in 1 and 3 positions. Okay, we start counting here in 1 substituent, 1, 2, 3. However, if we count the opposite, we can have 1, 2, 3.5. Which is lower? Of course, this will be the right numeration. That means that this will be 1, 3 dimethyl, because both are the same, dimethyl, cyclohexane. Then remember that we have alphabetical priority. That means this will be 1 ethyl, 2 methyl, and not 2 ethyl, 1 methyl. Okay? This will be cyclopentane, 1 ethyl, 2 methyl, cyclopentane. halogens are exactly the same than alkyl groups. That means here we will have 1 bromo, 2 methyl cyclobutane. Here we will have 1 bromo. Well, what we cannot do is exactly this. Bromo is first because alphabetical. That means that this has to be 1, this has to be 2, not like this, like we put here. Take this example. We have 1, 2, 3, 4 substituents. Okay, we have 2 methyls, 1 ethyl, 7-member ring. Okay, that means by priority the number this must be ethyl. Okay, and the number 1 we put in this methyl because it's the lower priority possible. 1, 2, 4. Okay, if we put here is 1, 2, I will say 6 probably. If we put here is 1, 3, 4. All are higher than this. 1, 2, 4. Okay, this is 1 methyl, 4 methyl. That means 1, 4 dimethyl, 2 ethyl that we will put first because remember we put the substituents in the name by alphabetical order, and then cycloheptane. We cannot put any other name. Okay, this is okay. Please do this exercise at home. If you have any problems, send me an email. Okay, we can remember the cis-trans isomerism in cycloalkanes. Okay, for example, we have here this ethane. Obviously, this carbon and this carbon, this sp3 carbon has free rotation. Okay, we can rotate and we can get this compound. However, when we have a cycle, the rotation is restricted. That means we cannot rotate this angle because if we rotate this angle, we break these two bonds. Cannot be possible. That means that cyclopropane, has a fixed structure. Cycloalkanes has two phases. Here you can see we have a phase over the triangle and a phase in the bottom of the triangle. And we can put the substituents up or down. And this up or down cannot be transformed by a rotation. We cannot rotate this angle in order to put this up. If we rotate this angle and we put this up, we break these bonds. Basically, we cannot do it. That means that we can dispose these two substituents, these two methyl substituents, in two different shapes, both in the same side or one in each side, or both in the top face and one in each face. In the top, one in the top and one in the bottom face. Okay? Here are constitutional isomers. Here what we have is stereoisomers. If you check the bond, the matrix of the bonds is exactly the same. We don't change anything. Each carbon is bonded with exactly the same carbon in both structures. The only change is the 3D shape. Okay, we can have both up or both down. If we have the both substituents in the same direction, both up or both down, what we have is a cis configuration. We say that this is a cis configuration, both in the same side. In a similar way what we said with alkenes. Okay? If we have both substituents in different sites, what we have, or what we say, or what we name, is that we have a trans substitution. Okay, that means this compound will be 1,3-dimethyl cyclobutane, if we follow the nomenclature that we did before. But now to identify that the bows are up, we will put cis, and normally this cis is in italic, 1,3-dimethyl cyclobutane. In this case, exactly the same. This will be a 1-bromo-3-ethyl cyclopentane, But to identify that we have each substituent in one site or in one phase, what we say is that it's a trans 1-bromo 3-ethyl cyclopentane. Okay, this indicates the relative configuration between the substituents. Cis, both are in the same site. Trans, the two substituents are in different sites, different phases. Okay, please do this exercise and you will see that it's quite easy. What about the ring strain, the stability of cycloalkanes? Well, we know that the carbon normally has a bond angle of 109. If we are doing a cyclopropane, what we have is we have a 60 degrees angle between the two substituents of one carbon. Why? Because it's geometry. If we are forming a triangle, this triangle is 180 in total, divided by between 3 angles is 60. That means that this angle between these two bonds of the carbon will be 60. In the case of cyclobutane, will be 90. In the case of cyclopentane, will be 100 something. In the case of cyclohexanone, will be 120. That means, in all the examples that we saw, when we have small rings from 3 to 6, what we have is that we have a deviation of the angle. Adolf von Bayer, our friend, suggested small and large rings might be unstable due to angle strain. That means, obviously, if the normal angle is 109 and we are using 60, obviously this poor angle will have some strain. He will like to have 109 and not 60. This can be found in the amount of strain versus the head of combustion. You can see here that 3 and 4 rings has a head of combustion higher than 5, higher than 6, higher than 7, and then we are increasing again until 10, and then after 10 what is happening is that the rings are so big that we cannot consider that are planar, and then we have different conformations and they can adjust the angle properly. Most cyclohexanes are not flat. This is the problem. They adopt puckered three-dimensional conformations that allow bond angles to be nearly tetrahedral. This happens with big rings, and is happening, for example, with the cycloalkane. Okay, we can define angle strain, the strain due to expansion of compression of bond angles. We can talk about torsional strain, the strain due to the eclipsing of bonds on neighboring atoms. Steric strain, the strain due to the repulsive interactions when atoms approach each other too close. Okay? Basically, the angle strain only occurs in C3, C4. Torsional strain and steric strain occurs between C7 and C11. Okay, we put an example, cyclopropanes. Cyclopropane probably is the easier ring because 3-member rings are always planar. There are no any other possibility. Has to be planar. Okay, this is the Newman projection, and what we have is that if we see the Newman projection, all the atoms, all the substituents are in eclipsed position. That means that this will increase the energy. Okay. If we get to the cyclobutane, what we saw is that the cyclobutane is not anymore planar. It's like a puckered conformation. Okay, it's bended a little bit. Okay, and we saw that are not really eclipsed, are close to eclipsed but not really eclipsed. That means they have less angle strain and more torsional strain. In the 5-member ring, we have a real puckered. This is like an envelope. Okay, the Newman projection, and now we saw that we have some eclipsing, are not really staggered or gouged, but okay, it's better than before. Planar cycloponten has no angle strain, but too much torsional strain. If we put planar, what is happening is what we have is everything eclipsed. Okay, and then to minimize energy, adopt a Pucheret conformation that has more angle strain but has less torsional strain, because these atoms are, the angle between these two atoms is bigger. That means that in total we have less strain. Okay, and here is the cyclohexane. The cyclohexane is the 6-member ring. Formally, the angle has to be 120. However, they can take this Pucheret conformation that is called a chair. Okay, this chair is a strain-free chair conformation. Why? Because when we Pucheret, the angles are more or less 109. And importantly, if we do the Newman projection of the substituents, all the substituents are in perfect staggered situation. Okay, are not eclipsed, are in staggered, except perfect. That means that zero strain for angular strain and zero strain for torsional strain. Okay, here you can see how to grow the cyclohexane. I show you in class another way to grow the cyclohexane. Do whatever you want. For me, any cyclohexane should be correct. Okay. Also, we can think that the cyclohexane can have a twist-boss conformation that is almost nearly free of angular strain. Okay, this conformation, like a boat, is no angular strain. However, now what is happening is that this substituent and this substituent are crashing, are very close in space. That means that we are increasing the steric strain, making this more unstable. This is why the chair conformation is exactly the best conformation for the cyclohexane, and this is translating directly in the sugars. If you study sugars in the future, or you study sugars, you will see that all the sugars has a chair conformation. All the sugars of 6-member ring. Here it is. Okay. This is the cyclohexane with all the substituents. This is the sugar. Okay, that only that we substitute the CH2 by oxygen, and then we put all the substituents. If we analyze this chair conformation, what we can see is that we have two different positions. We have the axial positions that are going up and down, symbolized here by the red hydrogens, and we have the equatorial position symbolized by the blue hydrogens. Okay. When we have axial substituents, what is happening is that these axial substituents, okay, generate interactions between the other two axial substituents in the same phase. That means the interaction between this and this is called a one-free biaxial interaction, okay, and destabilize the molecule. The equatorial bonds are going each one in one direction and are totally stable. Okay. Here basically is showing you how to draw the different equatorial and axial bonds and differentiate. Why this is important? Because both positions, as I explained before, are not equivalent. Okay? If we put a substituent in the axial position, we have interactions between this position or this position and this position. Okay, for example, we use the bromine. Bromine here, this bromine will interact with this hydrogen and this hydrogen, destabilizing the system. However, when it's in equatorial, you can see that the bromine is far away of everything. That means that no interaction. What we can get from this? Well, that if this is more unstable than this, in the equilibria, we will have always the most stable compound will be the compound that has the bigger substituents in equatorial position. Two conformations of a monosubstituted cyclohexane aren't equally stable. A substituent is always more stable in an equatorial position than in an axial position. Is what we explained. Here you have a metal here. This metal is interacting with these two protons, destabilizing by steric strain this structure. But if the substituent is in equatorial position, we don't have any one free diaxial interaction. What happens if we have two different monosubstituted cyclohexanes? Okay, well, this is the one free diaxial strain with the energy. You know, it's mathematics. If we have a substituent here, you check the substituent that is here. Okay, for example, now we are comparing any substituent with a hydrogen, and we saw how much energy is required to have this axial substituent. For example, if we have fluorine is 0.5, if we have a bromine is 1, I guess, etc. The only that we need is to sum this with this with this, and we will know the extra energy that is required. For example, we have a cis-1,2 dimethyl cyclohexane. If we have a cis-1,2 dimethyl cyclohexane, here we have the growing. Obviously, if it's cis, one has to be up, the second has to be up also. That means that we can grow it in these two different conformations. In these two different conformations, what we have is one gauge interaction between this CH3 and CH3. Okay, and that's all. We can grow the two different cyclohexane conformations, but both will be exactly the same. Always we will have one metal in equatorial, one metal in equatorial, and one metal in axial, one metal in axial. Okay, but what happens if we have a trans 1,2 dimethyl cyclohexane? Okay, in a trans 1,2 dimethyl cyclohexane, we can grow this form where the cyclohexane, the both substituents are in equatorial. Okay, or we can grow this where both substituents are in axial. Which will be more stable? Obviously the one that has the two substituents in equatorial. Why? Because we don't have one free diaxial interaction. That means this methyl is interacting with this hydrogen is interacting with this metal, destabilizing the system. Here, these two metals are far away of everything. Okay? Here, you can see the energies for different substitutions. Okay? But basically, remember that always, if we can, we have to put the major part of the substituents in the axial, in the equatorial position, that is more stable. Okay, thank you very much for your attention, and see you next day.